Welcome! In this session, we'll be exploring a fascinating problem from LeetCode, problem number 758, titled Bold Words in String. This problem is a great opportunity to enhance your understanding of string manipulation and algorithmic thinking. Let's dive in and uncover the best approaches to solve this challenge. In this problem, you're tasked with taking an array of strings, called words, and a longer string S, and identifying all substrings in S that match any of the words in the array. Once identified, these matching substrings need to be enclosed in bold tags, specifically B and /B. A key aspect of the problem is handling overlaps. If two substrings overlap or are contiguous, they should be combined into a single bolded section. Additionally, the bolded region should be output as one continuous string, without introducing extra spaces. The input constraints for the problem are fairly straightforward. The words array can have up to 100 strings, each with a length between 1 and 100, while the string S itself can be up to 10,000 characters long and contains only lowercase English letters. The goal is to return a modified version of S with the appropriate substrings wrapped in bold tags. To understand how this works, let's look at the first example. Here, the input array words contains the strings ab and bc, and the string S is abt. In the output, we see the result is BAABC/B greater than D. But why? The substring ab from words appears starting at index 1 of S, and the substring BC starts at index 2. Since these two substrings overlap, they share the character B, they are merged into a single bolded section, which is AABC. The rest of the string, the character D, remains outside the bold tags. So, the final result combines these elements neatly into the string BAABC/B greater than D. The second example illustrates a different scenario. Here, the input words contains ABC and 123, while the string S is abx is 123. The output is BABC/BXYZ B123/B. In this case, the substring ABC appears at the very start of S, and 123 appears near the end. Since these two substrings are separate and do not overlap, they are bolded independently. The result is a string where ABC is bolded at the beginning, followed by the unmodified middle portion XYZ, and then another bolded section for 123 at the end. This example demonstrates how non-overlapping matches are handled distinctly. The third example shows how individual characters from words can also be bolded if they match. Here, words contains the single character strings A, C, and E, and S is ABCDE. The output is B greater than A/B greater than B less than B greater than C/B greater than D less than B greater than E/B. Each character in words matches a specific position in S, A at index 0, C at index 2, and E at index 4. Since none of these matches overlap, each one is wrapped in its own pair of bold tags. The rest of the string, like the characters B and D, remains unmodified. This example highlights how the solution handles cases with multiple distinct matches spread across the string. Finally, let's consider the constraints and a few edge cases. The constraints restate that the length of words is between 1 and 100, each word in words is at least one character long and at most 100, and the string S can be up to 10,000 characters long. It's also essential to note that overlap must always result in a single bolded section. For example, if words is empty or no matches are found in S, the output remains unchanged. Additionally, when substrings fully overlap, like in the case where words equals A, AB, and S equals ABC, the longer match takes precedence, resulting in a merged bold tag. Lastly, if the entire string matches a single word in words, the entire string is bolded. These cases ensure clarity around how to handle the input strings in edge scenarios in the problem. To solve this problem, we initially considered two approaches. The first is the brute force method, where the idea is to iteratively check every possible substring of the string S against each word in the list words. If a match is found, the corresponding indices in the string are marked as bold, and later, we wrap these bold regions with B tags. To implement this, we can use a simple method like s.find to locate occurrences of each word in S. While straightforward, this approach has a significant drawback. Its time complexity is k*n squared, where k is the number of words and n is the length of S. This is because we repeatedly scan the string for each word, which becomes prohibitively slow for larger inputs. Alternatively, we explored a more optimized approach that also uses a Boolean array to track bolded indices. Instead of repeatedly scanning the string, this method processes all words in one pass to mark the indices directly. We then merge consecutive bold regions into a single B tag during post-processing. This reduces the complexity to O(k*(n), making it significantly more efficient while still being relatively simple to implement. However, it does require additional space for the Boolean array. Another approach we considered involves using a tree, or prefix tree, to pre-process the words in the list words. The intuition here is that instead of searching the string S for each word individually, we can build a tree to optimize substring searches. This allows us to leverage prefix matching to efficiently find all occurrences of words in S. The process begins by constructing the tree from the words list, which takes O(m), where m is the total length of all words. Then, for each character in S, we traverse the tree to locate matches starting at that character. As matches are found, we mark the corresponding indices in the Boolean array as bold. Afterward, these bold regions are merged into B tags. The overall complexity of this approach is O(m) plus n*L, where L is the average length of the words in words. While this method is highly efficient for large or repetitive word lists, it does come with pre-processing overhead. It's most suitable for scenarios where the list of words is very large and needs to be reused across different strings. Ultimately, the chosen strategy is the optimized approach using a Boolean array. This decision was based on some key observations. First, the problem requires merging overlapping bold regions, which can be handled elegantly using a Boolean array. Second, while the tree-based approach offers higher performance for certain cases, it introduces additional complexity that isn't always necessary, especially for typical input sizes. Lastly, the brute force method was ruled out due to its inefficiency for larger inputs. The breakthrough insight was recognizing that a Boolean array simplifies the merging of ranges while avoiding redundant computations. This approach strikes a balance between simplicity, efficiency, and ease of implementation. It is practical, easier to debug, and performs well for most cases. In terms of complexity, the time complexity is O(k*(n), where k is the number of words and n is the length of S. The space complexity is O(n), which is used for the Boolean array. Overall, this method provides a clean and effective solution to the problem. To solve the problem, we need to identify substrings in the string S that match any word in the words list and wrap them with B tags. If these bolded substrings overlap or are contiguous, they must merge into a single tag. The first step in our algorithm is to initialize data structures. We use a Boolean array called bold, which has the same length as the string S. Each entry in this array will track whether the corresponding character in S is part of a bold substring. Initially, all entries in bold are set to false. The next step is to mark the bold intervals. For each word in words, we use a sliding window technique to find all occurrences of the word in S. When a match is found, we update the bold array to mark all indices corresponding to the characters of the word as true. This process ensures we efficiently locate all matches while keeping track of bold regions in a straightforward manner. After marking the bold intervals, we move on to merging bold regions. This involves traversing the bold array to identify contiguous segments where bold I is true. For each of these regions, we record the start and end indices to represent the bolded substring. Once the regions are identified, we construct the final string by iterating over S and inserting B tags at the start and end of each bold region. Overlapping or contiguous bold intervals are automatically merged during this process, ensuring we avoid unnecessary or redundant tags. This structured approach gives us the desired output with all matching substrings properly highlighted. There are a few key insights that make this algorithm efficient and robust. First, using a Boolean array is an effective way to track which characters need to be bolded without modifying the string S directly. This avoids repeatedly concatenating strings, which can be computationally expensive. Second, handling overlaps and contiguity is simplified by marking bold regions in a single pass over the bold array. This eliminates the need for additional logic to merge overlapping substrings. Finally, the sliding window technique, such as using s.find or a manual search, allows us to efficiently locate all occurrences of a word in S. By avoiding redundant checks, we ensure the algorithm performs well even with longer strings or larger word lists. When implementing this algorithm, it's important to account for edge cases. For example, words in words may overlap within S, or bold regions might extend to the very beginning or end of the string. We also need to handle cases where S is an empty string, or words is an empty list. Additionally, some characters in S might not match any word, and these should remain unaffected in the output. To support this, we rely on two primary data structures. The Boolean array bold allows us to efficiently track which characters should be bolded, with a size proportional to the length of S. Meanwhile, a string builder is used to construct the final output string. This avoids the inefficiency of repeated string concatenation, which can significantly slow down performance for larger inputs. Analyzing the complexity of this algorithm gives us a clear understanding of its efficiency. In terms of time complexity, for each word in words, we scan the string S to find all occurrences. If n is the length of S and k is the number of words, the worst-case complexity is O, n asterisk k asterisk m, where m is the average length of the words in words. Constructing the final string involves a single pass over S, so the total time complexity remains O, n asterisk k asterisk m. For space complexity, the bold array requires O, n, space, and the string builder's space usage depends on the output size, which is also O, n. Therefore, the overall space complexity is O, n, making the algorithm both time and space efficient. Let's walk through an example to see the algorithm in action. Given the input string S equals abc is 123 and the word list words equals abc 123, we start by marking bold intervals. The word ABC is found starting at index 0, so we mark bold 0:3 as true. The word 123 is found starting at index 6, so we mark bold 6:9 as true. This results in the bold array being true, 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 false, 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 true, true, true. Next, we merge the bold regions based on this array. The bold segments are identified as 0, 3, and 6, 9. Finally, we construct the output by wrapping these regions with B tags. The result is BABC/BXYZ B123/B. This example demonstrates how the algorithm efficiently processes the input to produce the desired output while handling bold regions seamlessly. Here, we define the bold words method within the solution class. The goal of this method is to add bold tags around words in the string S that match any of the words given in the words list. First, we initialize n to the length of the string S and create a list called bold of the same length, initialized to false. This list will track which characters in S need to be bolded. Next, for each word in the words list, we use the find method to locate its occurrences in S. The find function returns the starting index of the word, or -1 if the word is not found. If the word is found, we loop through its characters, marking the corresponding indices in the bold list as true. We then continue searching for the next occurrence of the word by calling find again, starting from the position after the current match. This ensures that all occurrences of each word are accounted for. Once this process is complete, the bold list will indicate which characters in S need to be enclosed in bold tags. With the bold list prepared, we now construct the resulting string. Using a while loop, we iterate through the string S. If the current character needs to be bolded, as indicated by the bold list, we append an opening B tag to the result list. Then, we continue appending all consecutive bolded characters from S until we encounter a non-bolded character, at which point we append a closing /B tag. If a character does not need to be bolded, we simply add it to the result list as is. Finally, we join all elements of the result list into a single string using the join method and return it. This ensures that the output string has the correct bold tags applied around the specified words. Here, we start by importing the necessary packages and defining our solution class. The method boldWords takes in two inputs, an array of words and a string S. First, we determine the length of the string S and initialize a Boolean array called bold with the same length. This array will help us track which positions in the string need to be bolded. Next, we iterate through each word in the words array. For every word, we use the index of method to find its starting position in the string S. If the word is found, we mark its corresponding indices in the bold array as true. This is done using a nested loop that iterates through the length of the word. Additionally, we use a while loop to handle cases where the word appears multiple times in the string, finding the next occurrence by calling index of again with an updated starting position. Once all the bold positions are marked, we proceed to construct the resulting string with B tags. To build the result string, we use a string builder object and iterate through the string s using a while loop. If the current position in the bold array is marked as true, we append an opening B tag to the result. Then, we continue appending characters from the string s as long as the bold array remains true, effectively grouping consecutive bolded characters together. Once we exit the inner loop, we append a closing /B tag. On the other hand, if the current position in the bold array is false, we simply append the character at that position to the result. This ensures that non-bolded regions of the string are handled correctly. After processing all characters in the string, we return the constructed result as a single string. This implementation efficiently combines marking positions and building the final string, ensuring the proper placement of B tags around the specified words. To solve the problem of wrapping bold tags around specific words within a string, we start with an example where the input words array contains ABC and 123, and the string s is x is 123. First, we initialize a variable n to represent the length of s, which is 9, and create a bold array of the same length with all values set to false. This array helps us track which characters in s need to be bolded. Next, we iterate through each word in the words array. For the word ABC, we find its starting index in s using s.find, which returns 0. We then mark the positions from index 0 to 3 in the bold array as true. Since there are no further occurrences of ABC, we move to the next word, 123. Here, s.find gives the starting index as 6, so we mark positions from index 6 to 9 as true. Once again, there are no additional occurrences, so our bold array now reflects the positions corresponding to ABC and 123 as true while the rest remain false. The next step is to construct the result string based on the bold array. We iterate through the string s and use the bold array to decide where to add B and /B tags. At index 0, since bold 0 is true, we append a B tag and continue adding characters until bold I becomes false. This gives us the substring BABC/B. At index 3, the bold value is false, so we append the characters XYZ without any tags. Then at index 6, the bold value is true again, so we add another B tag and include the characters 123 before closing with a /B tag. The final result is BABC/BXYZ B123/B, which correctly wraps the specified words in bold tags while leaving the rest of the string untouched. Now let's consider a slightly more complex case where the words in the words array overlap. Here, the input consists of words as UB, BC, and the string s as ABCDE. We begin by initializing n to 5, the length of s, and setting the bold array to all false. For the word UB, we find its starting index in s as 0 using s.find. This allows us to mark the indices 0 to 2 in the bold array as true. Next, we move to the word BC, which starts at index 1. We mark indices 1 to 3 in the bold array as true. Notice that this creates an overlap where both words contribute to bolding the B and C characters. With no further occurrences of these words, the bold array now accurately reflects the positions that need to be bolded. To generate the result string, we again iterate through s and use the bold array to decide where to insert bold tags. At index 0, since bold 0 is true, we append a B tag and continue adding characters until bold I becomes false, which gives us BABC/B. At index 3, the bold value changes to false, so we append the remaining characters to without any tags. The final result string for this example is BABC/BDE, which correctly handles the overlapping matches by ensuring the bold tags are placed only once for the overlapping regions. Finally, we consider an example where there are no matches. Here, the input words array contains XYZ, and the string s is ABCDE. After initializing n to 5 and the bold array to all false, we attempt to find the word XYZ in s. Since s.find returns -1, indicating no matches, the bold array remains unchanged. When we build the result string, we iterate through s and observe that all values in the bold array are false. As a result, we append all characters of s without adding any tags. The final result is simply ABCDE, which reflects the absence of any bolded sections in the string. To analyze the time complexity, we start by looking at the two main steps of the solution, marking the bold positions and constructing the result string. First, during the marking step, the algorithm iterates over all the words in the words list. Let's say there are m words in total. For each word, the algorithm uses the s.find word operation to locate its occurrences in the string s. This find operation takes n time, where n is the length of s, because it scans through the string to find a match. If there are multiple occurrences of the word, the find operation is repeated, making it a significant contributor to the overall complexity. Once a word is found, the algorithm marks the corresponding indices in the bold array. This marking involves iterating over the length of the word, which takes len word time for each occurrence. When we combine these steps, the worst-case time complexity for this marking process becomes m*n, assuming the words are relatively short compared to n and may occur multiple times in s. Now let's move on to the second step, building the result string. In this step, the algorithm iterates through the string s once, checking the bold array to decide where to insert the b/b tags. This linear pass is an n operation since it processes each character of s exactly once. Additionally, appending characters and tags to the result list is done in constant time per operation, and joining the list at the end is also an n operation. Therefore, the time complexity for this step is n. When we combine the complexities of the marking step and the result construction step, the overall time complexity is dominated by the m*n marking process. This gives the total time complexity of the solution as m*n. Next, let's analyze the space complexity of the solution. The first significant space requirement comes from the bold array, which stores a Boolean value for each character in s. Since the length of s is n, this requires n space. Then, there is the result list, which temporarily stores the final output string with the added b/b tags. In the worst case, the result string could be nearly twice as long as s because of the additional tags, but this still scales as n. Beyond these, the algorithm uses a constant amount of auxiliary space for variables like start, I, and other counters. Therefore, the total space complexity is n, as the bold array and result list dominate the space usage. If we compare this solution with a brute force approach, the brute force method would involve checking every substring of s against the words and words, leading to n squared substrings and a time complexity of m*n squared. In contrast, the current solution optimizes this to m*n by efficiently locating substrings using the find operation. Finally, let's examine the best, average, and worst-case scenarios for this algorithm. In the best case, if the words list is empty, the algorithm only needs to process the string s, resulting in an n time complexity. In an average case, if words contains a small number of short words that occur infrequently in s, the complexity is closer to m*n, as the marking step remains efficient. In the worst case, if words contains many words that occur frequently throughout s, the marking step could reach its maximum complexity of m*n. Mathematically, the use of s.find word ensures that locating each word in s takes n time, and processing all m words scales linearly with m. This gives the overall time complexity of m*n. The space complexity remains linear in n, due to the space required for the bold array and the result list, which is independent of the number of words m. When solving this problem, there are a few common mistakes to watch out for. First, failing to handle overlapping ranges is a frequent issue. If you mark bold ranges independently and don't merge overlapping intervals, you could end up with split or redundant b tags. For example, if you have ranges 2, 5, and 4, 7, these should be combined into a single interval, 2, 7. Not merging them can lead to incorrectly formatted output. Another common pitfall is inefficient substring matching. Using nested loops to compare every substring of s with each word in the words list can result in extremely poor performance, with time complexity as bad as n cubed for large inputs. Instead, optimized techniques like tries or KMP can help scale better. Lastly, it's important to account for case sensitivity. Some problem variations require case-insensitive matching, so failing to convert both s and words to lowercase before processing can lead to mismatches. Always ensure you're handling this based on the given constraints. Another frequent mistake involves incorrect b tag placement. If you don't carefully merge ranges, you might end up with overlapping or unclosed b tags, which can break rendering in HTML. Properly formatted tags are essential to ensure the output is valid and renders as expected. Additionally, ignoring edge cases is a critical oversight to avoid. Examples of edge cases include scenarios where s or words is empty, when none of the words match, or when the entire string s needs to be bold. Failing to account for these special situations can lead to runtime errors or incorrect results. Robust solutions require thorough testing and handling of all edge cases to ensure reliability. Lastly, always keep in mind that addressing these details not only avoids errors but also demonstrates a thoughtful and complete approach during interviews. This problem is a great example of how recognizing patterns can save time and effort. At its core, it involves two fundamental patterns: interval merging and substring search. Identifying the need to merge overlapping ranges early on is crucial for success. For substring search, brute force methods are inefficient, so leveraging optimal techniques like tries or Rabin-Karp hashing can make a big difference in performance. Beyond the algorithm, it's important to test edge cases thoroughly and ask clarifying questions when solving the problem in an interview. For instance, you should confirm if empty inputs or overlapping matches need special handling. Additionally, be prepared to discuss the time complexity of your solution. For example, a tree-based approach achieves O, n plus m, complexity, where n is the length of s and m is the total number of characters in words. It's also essential to clarify constraints, such as whether case sensitivity matters, how to handle special characters, or if words can contain duplicates. Finally, it's helpful to connect this problem to similar ones, such as LeetCode 56 for interval merging, or LeetCode 208 for implementing a tree, which can deepen your understanding of the underlying patterns. There are also alternative approaches that can be valuable depending on the specific constraints of the problem. One such option is the tree-based approach, where you insert all the words into a tree and use it to efficiently find matching substrings in S. This approach is particularly fast for large inputs, but the trade-off is the additional memory required to store the tree. Another option is Rabin-Karp hashing, which uses a rolling hash to search for substrings in O, n plus m, time. This method avoids the need to build a tree, but it requires careful implementation to ensure the hash function works correctly and handles collisions effectively. A third alternative is using an interval tree for range merging. This structure enables dynamic merging of overlapping ranges, which can be useful in scenarios where ranges are updated frequently. However, implementing an interval tree is more complex and may not be necessary for simpler cases. By understanding these alternative methods, you can choose the one that best fits the problem's constraints and requirements. Great job! Today, we learned how to solve the bold words in string problem using efficient techniques. Remember to keep practicing string manipulation challenges to sharpen your skills. Don't forget to like, share, and subscribe for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!